cost for the entire system. All right. Yeah. So that is good news. But then you also saw that there was a lot of costs associated with the flexible generation. So where are we today? That's the critical part. Okay. So before we go into the PJM itself, I'll just take a quick detour. So we did a study. Well, let's see what happened in the U.S. in general. And so the chart to the left is the large subcritical coal fleet. And the 2000 to 2020 period, you can see, because historically large subcritical coal units would operate at full load, base loaded, you can see that yellow bar, 65% of the time they were close to running at full load. They would stay offline about 10 to 13%, and they would perform like low load operation about 19%. You look at the recent few years, you can see that's changed, so they're not operating at full load all that much. The biggest change is that they're going and changing load all the time to account for the could be renewables, could be prices, could be a lot of other things. So that's interesting. Now, this is the chart to the right is true because we published this a few years ago, and then I think this is now true, especially for PJM, is even the combined cycle fleet has evolved. We call it the conventional combined cycle fleet. So these were the units that were built in the late 90s, early 2000s, typically GE 7F machines, typical combined cycle machines. They are behaving more and more like coal plants. Then we have the fast start combined cycle machines. There was only a handful of them that were ever built, just a few of them. And they're very specific to certain markets. California is obviously one place why this happens. And the reason is, California is a solar heavy state. So you need that big, flexible ramping capability. And so that's why, California has that. And then we've started to see high efficiency combined cycles come on the grid. There's quite a few in Louisiana, Texas, certainly quite a few on the East Coast. And they are running properly like baseload units, like conventional baseload units. So what does this do? This is the PJM grid now. So, what's fascinating about the PJM grid is that, I showed 2005 all the way to 2023. So, so we did the study around the 2011-12 period, and we said, okay, yeah, coal and gas were about 60% off, the mix. Nuclear obviously was dominating. And then you see all the way to 2023, and you can see natural gas has kind of displaced the coal capacity, and certainly the energy that comes out of the coal units. And the renewables haven't quite made that much of a mark on the PJM grid. So while we talk about the energy transition, there's clearly a transition. There's like an intermediate step, the bridge here on the PJM grid, with natural gas dominating for a number of years now. So we'll see what happens in the future. But as we talk about this, let's see what else happened on the grid. And hopefully you can type in questions if you see it, or you want to add. We can certainly talk at the end. So in terms of start, clearly we can see what we had predicted in the analysis is what is happening. So overall, we know that the flexibility requirements are increasing. That's the the median line in the blue, but not that much, so not as dramatic as we had expected from the simulation. And then you can see the yellow line is the worst case scenario, the 90th percentile. And then you can see also from the significant load changes. So the load following that we were talking about is rather modest in this case when we look at the actual data of what actually happened. And then there's some analysis on, okay, well, we know there's some distinct operating profile. So how gas and coal is operating, there's certainly differences. So back in 2012, we had about 10 to 15 average annual starts, and that's gone up a little bit for for the gas units, and then the coal units are shifting a little bit, but not the dramatic changes that we were expecting. And so when we look at the average values, we see only a 13% increase in the amount of flexible generation from coal plants and about a 36%. So nowhere close to that 100 or 200% that we were talking about, though you can imagine that we haven't reached that level of renewables that the study was looking at. But here's what's interesting with PJM. With PJM's grid alone added 33 gigawatts of natural gas-fired capacity between 2014 and 2022. So it's a little different, assessment than we normally are used to looking at in terms of renewable changes. So for the larger units, I was saying, there's modest changes. The combined cycle fleet, I just want to point out the scales are a little bit different, but by and large, not much change over the years as these units have operated. You would expect, as you add a little bit more renewables, you will see some increase in simple cycle CT operation, but small coal is seeing the biggest change. And I'm going to skip through and just talk about, when we are doing these studies and analyses that we might not have thought about all the possible uncertainties in the analysis. We do our best case of we try and take everything into account, but there's always something that will trip us up, and that's what happened in a little bit in this study. So here's an interesting way to look at all of this, is that in fact, so because of how these units are operating, that actually the subcritical coal units, and we've done analysis for PJM, there's a very good chance that the remaining coal fleet, unless you're brand new and super efficient, the ultras or supercritical units, there's a few in PJM, that they're likely to not run for the next 10, 15 years. So which means that actually their cost of flexibility actually goes down in the short run, because they're going to get retired at some point, and so you don't have the extra cost. All the other units see a slight increase in cost. So what we have done is provided, and there's a link here. So we do this for the Western Interconnect. We provide data to WEC on what is this cost, because this flexibility is important. And so we've actually added the typical combined cycle, the high efficiency combined cycle, and the fast start machines, all to give you a sense of what is this cost. So this is the cost per megawatt capacity, lower bound, for each of these generation technologies. So you would have these numbers if you ran a simulation or wanted to see what was going on with these units. So, okay, I spent quite a lot of time walking you through some of this renewable integration work that goes on, because we're not going to get through a complete energy transition unless we are able to accept a huge amount of renewables on the grid, and they could be utility scale or at people's homes or industrial C&I level, but everything has to work together. So we are making progress. So let's go to the overcoming the hurdles. Now, we know it's going to take a lot of money, and so I listed quite a few of these examples. I like the last one the best, the Energy Transition Commission's numbers. But if you look at McKinsey, it says we'll need $9.2 trillion. The IEA says $4.5 trillion. The number might be somewhere in between. S&P Global says renewable energy investment is going to be about 700 billion. So lots of numbers out there. But if you look at the Energy Transition Commission, it kind of says it depends. If you're going to high-income economies and China, they'll need a different amount of investment than, say, some other countries, and that's important to note. And then I came across a number of these numbers where you see basically there's an $18 trillion capital gap. So you talk about the Inflation Reduction Act or the Jobs Act. There's a lot of money being spent, but even despite that, there's a huge gap between what is actually needed than what is actually being spent. So, let's see how much progress we'll be able to make. So let's talk about the technology solutions to this. So revisiting smart grids, because I told you that smart grids have been in the zeitgeist for well over a decade now, and there are some cautionary tales around that, and the expectations versus the deliverables were not always matched together. So if you look at that recent New York Times article, it says a new surge in power use. We need too much power. But I just showed you the Silicon Valley power case. Or if you, I didn't want to put too many slides here, but if you look at the Norway case, where there's a huge increase in EVs in Norway, but they haven't, there's a projection that might need $1 billion over the next, 4 or 5 years to upgrade the grid. But it's not as doom and gloom as some of the preliminary analysis shows. Also, the reason why I wanted to show you about that simulation model is that oftentimes, it's the energy transition is going to be long and incremental in nature. It's not going to be a switch. And so we have time to prepare. We have reasons to do things the right way over time. And yes, we don't have hundreds of years to transition, but I think if you look at the past history, it's a good judge on what's likely to happen. So in terms of, metering infrastructure, so if you were, in this industry in the early 2010s or, 2008, 9, smart meters got really bad reputation in the beginning for all kinds of strange reasons. But, take 10 years out, and now 72% of all electric meters in the US are smart. So, give it time and you see the results. And there's two kinds of these things, right? I mean, so if you look at there's the AMI and the automated meter reading, which is only one-way communication, but, you really want to see the two-way communication to continue to trend up and get up to, 100%. So, I wanted to point that out. Cyber risk continues to be a vulnerability, and load forecasting is becoming quite challenging. There's a number of reasons for that, and I'll talk through that in a couple of minutes. So let's talk about the Excel Smart Grid City project. So I was fortunate enough to work on that early on in my career. So it's interesting. I put some slides from Excel Energy. It's hard to find them, but if you look for it, you'll find it. So the drivers for change back in 2008 are not all that different from the drivers for change today. You can look at a number of DOE or various utility IRPs and the likes. They have the same reasons for doing smart grids today that they had in 2008. First was grid reliability. They had aging assets. We have aging assets today. There's an increase in load, but the assumptions back in 2008 was you were still talking about 2-3% increase in load, not like today. Environmental reasons, absolutely. You've got the state mandates and global climate concerns, still true. Energy security, still true. Customer choices. I think this was a big reason and a good, big selling point for Excel back then was, that, hey, we're going to empower the consumer. We'll put the smart meters. We'll put the infrastructure around it. We'll give you data insights that, once you have all this information about your power use, that you would actually change your behavior on how and when you use your power. That was a big emphasis on empowering consumers. And back then there was not a lot of renewables, but certainly that was one of the things that they talked about was being able to better integrate the renewables. But if you look at the news reports today about this project, and I think and these are my personal views, is that they're a little bit too negative on all the lessons that were learned from this project. This is the first integrated smart grid. I remember we were co-optimizing virtual power plants, looking at demand response and putting into a optimization model on the best portfolio optimization of the time. Putting AMI infrastructure. Some of the technology decisions were not, didn't work out, but there were lots of great lessons learned. There was, that stakeholder engagement that I talked about early on was maybe lacking, but I would still give it, a good, B, not B plus, but a B grade on how well this implementation went. So virtual power plants, right? I mean, I mentioned we were talking about this in 2008. This is where we are today, 2022. We're finally scaling, but look at, there's a vast majority of the country where, no data either is available or not much is going on in terms of virtual power plants. But, there's more than 10, at least in a few locations. So, Texas, California, New York, and North Carolina have started to and then some others, Massachusetts, have started to utilize this. So, obviously in a Q&A, you can ask me more about the virtual power plants, but nothing special about what a VPP does. It's more of an aggregation tool. We use technology to, sign up a bunch of industrial users or home users to basically change their how much power they need at certain points in time, and you can sell that back into the market, and you benefit from having that flexibility. But my point about putting this slide here was, you would hope after all these years there'll be more use of this technology, and I know the DOE is certainly very optimistic about this case. So moving on. I want to talk one quick slide about carbon capture. So we're doing a number of projects around carbon capture. And so not all power plants are candidates. That's my bottom line here. So this is not, while there's discussion about, the role of carbon capture and energy transition, can we just go ahead and put this technology on power generators or the oil and gas refineries or whatever, anywhere where you see you want to capture and store the carbon. But when we do the analysis, we do bankability assessments on what is a good candidate for this. Is that if you take you're not going to put a carbon capture on an old aging coal-fired power plant, period. Because the reliability of the asset, which is what we are showing you on the left-hand side, is that we actually look at the likelihood of the reliability issues by system. Okay, so there's basically, if you put so many months of operation on a unit, that you're going to lose reliability on that asset over time, and so the carbon capture becomes less economically viable. And so this is an important aspect. The technology of carbon capture is not that is relatively mature at this point. There's certainly always improvements that can be made, but the technology is there. It's expensive, but it can be done. And so what we've ideated on, or we've sort of decided, like, this seems to make sense, is that the ideal candidate is obviously a large enough coal plant, if you're just talking about electric power plants, and right around, past the initial commissioning issues. So you're past the first 6-7 years of operation. So you're in that's the Goldilocks spot. So you're between age 8 to 14, 15. That's, so there's only a handful of coal plants then in North America that would be eligible, but that's your sweet spot. Those are the plants that will give you high reliability, the economies of scale, and and so you can actually make a case for carbon capture. All the other ones are expensive bets, and you don't, I gave you the cautionary tale of some other examples like the smart grid. So I'm more or less at the end of the discussion. So, electrification will play a major role. Significant investments are needed. You saw the trillions of dollars needed. Regulatory framework still needs to accommodate new technologies and business models. We talk about the smart grids or the virtual power plants. I mean, each of them present a new problem for the grid. And if you see lots of distributed resources are now behind the meter. And so, if I talk to utilities, some of the big problems that they have is coordination. So oftentimes they don't entirely always, I mean, unless more and more data is available, like we are doing with the smart meters, that there's more coordination required than control. Back in the day, the utility knew what assets it had. It could control how much they were producing with respect to what the demand was, and those things are getting a little bit more complicated today than they were before. And then public education and outreach. We don't want another bad implementation of one of these technologies. Is going to take a while, but it can be done. So I'm a little bit I have time for more Q&A. I can talk a little bit more, but I'm happy to take some questions.
Thank you, Nikhil. All right, so if you want, you can take it off the screen and just get people. As I mentioned at the beginning of the talk, thank you again, Nikhil. I'm going to open the floor to students. So students, please unmute yourself, introduce yourself, and then ask the question, and then go around the table to make sure all the students get their chance. And then I'll switch to the general audience for questions. All right? Questions from students? Questions from students? You'll get another opportunity in the next round. Oh, sorry, Andy, go ahead.
Hi, I am a work study student at the Energy Systems Engineering Master's Program. I was just wondering, you talk a lot about how these concepts and technologies has been out there for in the past and is now sort of being implemented today. And I was just wondering, why do you think it takes such a long time for these things to be implemented, and how do you think going forward that we should sort of fasten this process?
That's actually a great question, and I didn't want to give I don't want to give a pessimistic view of what actually happens. Maybe I should have been more gung-ho. If you look at trends of how much wind and solar and today's storage is being installed on, say, just a US grid, you can take grids around the world, and you just look at that trajectory. I think it blows my mind, the amount of wind and solar that gets installed. The reason why I showed you these different examples is that to say, not be a pessimist, but be cognizant that energy transition is going to take some time. It's not a switch. We can't just switch it over to something which would deliver all what we want, which is net zero emissions, and have totally thermal fleet free grids. It'll take time. So that was my point in terms of why it took some of these technologies so much time. I think the technologies existed. The scaling of that is interdependent on a number of things. One, 12 years ago, people were still building the technology for communication of this information. It took about a decade for these smart meters to get installed, to reach 72% of the US grid, right? So that it takes that much time. Again, that's one part of it. Two, people might blame the renewables, but the natural gas price being so low did not help the case, right? So what was the incentive to, at $2 an MBTU, the only thing that happened was that the coal plants got retired because they really ended up being more expensive to operate than the gas plants. So that did not help the case. So we are able to, so point is that the technology development takes time. I've only touched upon this. Interoperability is a big problem. So if you get a new piece of device in your home, so it's easy with our computers, right? You install a new software and you assume it's going to be backward compatible and forward compatible and all the drivers will work. The grid is a little bit more complicated and complex. So back in 2010, 11, I was in standards committees for automated demand response. It took 3-4 years for everybody to agree on what those standards were. Then it takes time for everybody to agree on building products. I mean, so I think it's just don't be a pessimist if you're a student. It just takes time, so you have more things to work on.
Thank you,
Got
Andy.
it. Thanks.
Questions from students? Please unmute yourself and introduce yourself. Shai, drop your question in the chat box and we'll get a chance to look at it. All right, I'm going to open the floor to the general audience. Questions for Nikhil.
Hi, Nikhil.
Alberto.
Yeah, so hi, Nikhil. Thank you so much for the presentation. That was very interesting. I had a question regarding like what you were talking regarding the cycling and ramping costs. Well, in systems like PJM, what you were showing is like renewables is still less than 10%, right? So like they're not seeing that much ramping.
Yeah.
Do you think, and this is kind of like a composite question. First, sometimes they've been talking about using more ancillary services, right? Like, so, and maybe that can accommodate some of that flexibility. Do we need new products or do we need the prices to go up, right? Because right now the prices of ancillary services are relatively low. So they probably don't provide a lot of the incentives that are required in order to, like, for example, install more capacity that is going to be flexible in the long run, right? Like more kind of like the adequacy question.
Yeah.
And so that would be the first question, right? Like, what do you think that is the overall trend that is going to be happening with ancillary services, whether there's going to be new products? Because like there was some discussion, but you have the finger on the industry in terms of like really what is the likelihood that new products are going to enter. And the second one is much more about the design itself. So like in certain cases, you mentioned VPPs, there's new actors that may have a little bit of flexibility, right? So they can help counteract some of these changes. Do you think that it could be, I mean, I guess I have like my bias, but do you think that like for conventional resources, do they prefer to have some kind of like a fixed payment for availability, kind of like a capacity market for flexibility? Or do they want to maintain volumetric according to whatever is the amount of flexibility that they deliver? How can we bring more of those resources online?
Yeah, it was great to see you again. We've exchanged notes several years ago, but your first question, that's already happening. So if you go to Ontario, where we work with a number of power producers. So Ontario, those of you who are not very familiar with the Canadian province, they used to have a lot of coal. They used to move power back and forth between New England, New York, and themselves. They certainly have nuclear, and they have hydro. Now, hydro, by definition, should be very flexible, is not perfectly flexible. There are reasons for that. You can't just flow water, down the river. If you've got number of constraints on that. So they shut down all their coal plants a few years ago. So they have zero coal. So they have nuclear, highly flexible nuclear. Bruce Power, you can take a look at how often it changes operation, changes load. And then they have these gas units. So to your point, they actually have a guaranteed cost guarantee program where you get a guaranteed, it's like a capacity payment. You get guaranteed payments for being available. if you come in California, you have flexibility mechanisms. So there's a, ramping up and ramping down, incentives for power plants to be able to actually perform that kind of ramping and get paid for it. So there are, I think there will be different markets that would have their own mechanisms being developed. Like, for example, when I look at Iowa, and you've done a lot of work in Iowa. Iowa is a great wind state. So you get almost 50% capacity factor on those wind resources. So even though it was traditionally a coal heavy region, all the wind that came online actually displaced the coal, and so they have a different incentive in that region than, say, for example, California, which is solar driven. So that was the first part. I think these mechanisms and these incentives will come into play, but they're not universal. We're not going to, I don't think it makes sense for one standard or one mechanism to be applied to different regions. And then, and the third one, like I mentioned, the Western energy imbalance market. I think that's a great idea. If different regions did that, to be able to move power and expand the area where you can get your power from and meet demand, I think that's a great mechanism without needing any other incentive like the each individual generator getting a certain incentive. So I think expanding the service territory by coordination and is probably a great idea. In terms of the flexible assets, the conventional fleet, I picked PJM. I should have, I realized I had a few more minutes. I could have picked California and Texas to show you some other analysis that we've done. I think conventional generators undersell the amount of flexibility they can actually provide. They have no incentive to provide more flexibility right now. So they are easily able to, and we've proven it time and time again, to operate in far more flexible mode than they have in the past. And if I think if they don't do so, if they are not that flexible, eventually they'll get displaced, just like the Iowa case, where you have high quality renewable resources, whether that could be storage or some other format. I wanted to talk a little bit about, there's long duration storage, a number of companies here that are doing that, or thermal batteries that would basically displace some of the conventional generator capabilities. But there's a lot of other things that are ongoing. And to Andy's question previously, right, these technologies will mature and you will start to see the conventional thought start to change. You can't just sit back and hope that the renewables will go away. They're going to keep coming and change the incentives for you.
Great, thank you so much.
Yeah.
Questions for Nikhil? General audience?
There's a question from David Ellis in the chat. How are VPPs different than aggregations that will be seen under the FERC 2222 in the future?
Yeah, that's a great question. I believe these are still evolving. I mean, there's I'm no expert on the FERC 2222 discussion, the order that came through. I think if you look at it up, you'd be able to get a better sense of it. My guess is fundamentally they're not all that different. I mean, if you look at it from a system perspective, the end use case of a virtual power plant, or you want to call it an aggregator, they kind of perform the same end goal. So I'll just say that, yeah, I think you'd be better. You'd have to research it yourself. I'm no expert.
Just a reminder, the next seminar will be about FERC 2222 by a manager from PJM. So I had heard that talk before, and it is not very different. Aggregation of VPP, to create a VPP seems to be an efficient way of getting renewables on the grid. questions for Nikhil?
Yeah, Rudy, this is Hal. I have a question.
Yes.
I have a question. Yes, I'm not surprised to see how natural gas has come into play because of the cost. What if we tax carbon? I know that's been around for a long time, that idea. Would that help drive everything towards more renewables?
I think so. I mean, I think renewables are going to grow despite taxation or other sort of, if you want to add a carbon tax, sure, that's likely to incentivize. I mean, but if you look at the Inflation Reduction Act and the likes, similar mechanisms around the world, renewables have a lot of incentives right now to be installed, and they are getting installed. But the only thing is, I would recommend all the students to take a couple of utilities and read their integrated resource plans. I think it's a great way to educate yourself about how utilities think about what the future looks like. And you just need a lot of capacity to displace the firm capacity that we get from conventional resources. So yes, I don't see how anybody puts a carbon tax in the current political environment, but yeah, it'll certainly help in that case, but you almost don't really need it. Renewables are cheaper to install and build than conventional resources. It'll just take time. PJM is just a unique case, and I wanted to point that out in this talk, that you take the example of India, for example. They've put a ton of renewables on the grid, but their demand has already been going up faster than the US. So during 2002 to 2020 to 2024, there was a drive to basically electrify every single village. And so all the system planning and everything went right out of the window, because once you install, provide electricity to all and each and every one of those farmers, they tend to put air conditioners and the likes in their houses. And so I think as the demand goes up significantly, the cost of renewables is trending lower and lower. It is cheaper already than conventional plants. That eventually, there will be more renewables on the grid. And yeah, I think that's what I'll say. I mean, the carbon tax, I just don't see how it'll actually happen.
Yeah, it'd be hard to implement. I understand. Thank you very much for the good answer. Thank you.
Sure.
Questions for Nikhil, please introduce yourself. Or drop the question in the chat box. So getting back to Alberto's question on ancillary services and market for it, do you think that with more use of energy storage, especially for states that are very ambitious about renewable integration, like New York and California, would that kind of put a higher value for ancillary services, because needing frequency management and voltage management would be more important?
Yeah, no doubt. And I think PJM's already had some big storage installs on the grid. I think even the energy storage will take time till we settle down on the ancillary services and the life of the storage asset itself. We've done analysis for PJM where, when they change their signal from, Reg A to Reg D, which, if you're a PJM expert, you know what the differences are, but that can have an effect on the battery life itself. So, while we are putting lots of storage on the grid, and again, I think just like the PJM case where natural gas seems to be the kingmaker there, storage is going to be dominant in certain parts of the grid where it gets really important. California, for example, and New York, and it'll certainly affect the ancillary services market and how those storage units are actually built. To previously Andy's question, I think it was a great question, is we're going to see a transition towards long duration energy storage. I don't know what the DOE calls it right now. I believe it's 8 hours or 6+ hours of storage. because today's batteries don't give you that 6 hours of operation. So even if you get the ancillary services, they're limited in nature. So there's a lot of different things that are happening that would impact each of these things that we've talked about today.
Question for Nikhil, please unmute yourself, ask the question. Or drop it in the chat box and we'll read the question. Question for Nikhil. Right. Again, thank you again, Nikhil, for your presentation. And just want to kind of let you know that our student assignment would be to put together a Zoomcast of each speaker, and we'll be glad to kind of show you what, that's a student assignment, that's their homework. And we'll be glad to share this with you. Thanks again for presenting, and I think very valuable data and lessons learned. And we look forward to a future talk from you. But then again, I want to let you know that next seminar is a great follow-up to some of the questions that were brought up about FERC Order 2222 and how they relate to virtual power plants. We'll have a manager, Daniela Krupp from PJM. She'll be talking about it 2 weeks from today. So look forward to seeing all of you in 2 weeks. And thank you very much.
Thank you.